Welcome. Let's talk about SiC power semiconductors in real designs when using silicon carbide, or SiC power semiconductors in practical applications. By end of this video, you will understand the need for an optimized DC link for SiC easy modules, understand the main effects of the parasitic elements in the DC link, and see the major aspects of connecting the DC link to an easy module. Ready? Let's dive in. To start, let's see a case of low inductance DC link connection. When dealing with advanced power electronics like wide bandgap devices, it's crucial to maintain a consistently low impedance across a broad range of frequencies. In cases where the impedance of the capacitors increases above the resonance frequency due to the parasitic inductance, the high switching frequencies and edge steepnesses require a low intermediate circuit impedance over a wide frequency range. You can achieve that by connecting different capacitors in parallel. And these would be a ceramic capacitor for a frequency range exceeding 1 MHz, a foil capacitor for switching frequency range from 10 kHz to 1 MHz, and an electrolytic capacitor. Pay attention to the parallel resonances that may arise during the design process. Typically, the resonance between the electrolytic capacitor and the foil capacitor is effectively dampened by the ESR, or equivalent series resistance of the electrolytic capacitor. Now, let's go through an example of a board layout for the EZ2B ANPC module. Let's get straight to the point. Take a look at this board layout example for the EZ2B ANPC module. Utilizing a multi-layer PCB is recommended to facilitate a low inductance connection of the capacitors to the EZ module. Employing a setup involving a direct connection of the ceramic capacitors to the DC pins has proven to be an advantage. When using the press-in device for the EZ module, it is essential to take precautions to minimize stress on the ceramic capacitors to prevent any potential damage. Next, you'll see an example of EZ3B ANPC. In this simplified equivalent circuit diagram, no additional vias for the ceramic capacitors were needed, so the other copper layers are not affected by the large creepage distances. For example, 5 mm per 1000 volts. This design approach does not reduce the copper cross-section available for connection to the other capacitors and the DC source on the other layers. Finally, one last example. Check out the good practices with the EZ2B half bridge. In the first design for a B6 inverter with unbalanced load capability, the ceramic capacitors were also designed as a split DC link circuit. This has the disadvantage of a higher leakage inductance L sigma 1, since 4 connection points to the PCB are necessary. The connection to the midpoint requires vias, which, in the example, leads to a reduction in the copper area for the current path to the source. As a result, increased heating of the PCB could be determined in the measurements of the prototype. The output filter already reduces the very high frequency components in this mesh. A version with a single ceramic capacitor with a direct connection to DC plus and DC minus would be a better solution at this point. To wrap this up, take note that an optimized DC link is crucial to maintain a consistently low impedance across a broad range of frequencies when using SiC easy modules. It's important to be aware of the effects of the parasitic elements in the DC link. And you can have different board layout when connecting the DC link to an easy module. The studies and tests shown in this video were brought to you by Fabian Schnabel, Daniel Strack, from the Fraunhofer Institute for Energy Economics and Energy System Technology, and Marco Jung, from this institute and the Bonn-Rhein-Sieg University of Applied Sciences. Hopefully this video was interesting and provided you some hints on SiC power semiconductors in real designs. If you need additional information, just have a look at our product page at Infineon.com.